Pfaffian differential forms and equations. The expression summation I varying from 1 to n fi into dxi, where the fi's are functions of some or all of the n independent variables x1, x2, etc. xn is called a Pfaffian differential form in n variables. Similarly, the relation sigma fi dxi equal to 0 is called a Pfaffian differential equation. This is also known as a total differential equation. In the case of two variables, we can express Pfaffian differential equation in the form p dx plus q dy equal to 0, where p and q are functions of x and y. This can also be expressed as dy by dx equal to minus p by q, which is a function of x and y and hence labeled as some f of xy. Here, since p and q are non-functions of x and y, we are given the functions p and q, so small f is also defined uniquely at each point of the xy plane at which the functions p and q are defined. So if these functions are single valued, then dy by dx will be single valued, so that the solution of the equation, which satisfies the boundary condition y equal to y naught when x is equal to x naught, consists of the curve which passes through the point x naught, y naught, and the tangent at each point is defined by the equation dy by dx equal to minus p by q. Thus, we can show that there exists exactly one function phi of xy such that phi of xy is equal to c, where c is a constant, defines a function y of x which satisfies the Pfaffian differential equation. If the differential form p dx plus q dy can be expressed as d phi, then we can say that this p dx plus q dy, this expression is exact or integrable. If that is not exact, then if phi equal to c is the solution, then dou phi by dou x into dx plus dou phi by dou y into dy will be equal to 0, and comparing this relation with p dx plus q dy equal to 0, we will get dou phi by dou x by p equal to dou phi by dou y by q equal to a function, say mu. Then we can see that mu into p dx plus q dy is equal to d phi, and that will be equal to 0. So the function mu is called an integrating factor of the Pfaffian differential equation, because on multiplication with mu, our Pfaffian differential form p dx plus q dy became exact. Thus, we have proved this theorem. A Pfaffian differential equation in two variables always possesses an integrating factor. Now, when there are three variables, Pfaffian differential equation can be expressed as p dx plus q dy plus r dz equal to 0, where p, q and r are functions of three variables x, y and z. Now, for convenience, if we write x bar, this bold x is a vector which can also be expressed as x bar is equal to the triple pqr and dr bar equal to dx, dy, dz. Using these vectors, we can express this relation p dx plus q dy plus r dz equal to 0 as x bar dot dr bar equal to 0, where dot represents the dot product of vectors. X bar dot dr bar will be p into dx plus q into dy plus r into dz, which is the LHS of this. So, Pfaffian differential equation can also be expressed as x bar dot dr bar equal to 0. Now, we have another theorem which states that a necessary and sufficient condition that there exists between two functions u of xy and v of xy. That means those two functions are functions of x and y. Then there will exist a relation capital F of uv equal to 0 connecting the functions u and v, which does not involve x or y explicitly, is that dou uv by dou xy equal to 0. That is, the Jacobian of u and v is equal to 0. To prove this, we first show that the condition is necessary. That is, we assume that there exists a relation capital F of uv equal to 0 which does not involve x or y explicitly. That means this expression does not contain x or y. So, if we differentiate this relation with respect to x using chain rule, we will get dou f by dou u into dou u by dou x plus dou f by dou v into dou v by dou x is equal to 0. Similarly, if we differentiate the same relation f of uv equal to 0 with respect to y, we will get dou f by dou u into dou u by dou y plus dou f by dou v into dou v by dou y equal to 0. Now, we can eliminate dou f by dou v from these two equations by multiplying the first equation by dou v by dou y, and we can multiply the second equation by dou v by dou x, and then we can subtract those two equations obtained. Then we will get this relation dou f by dou u into dou u by dou x into dou v by dou y minus dou u by dou y into dou v by dou x equal to 0. Since the relation 8, that means f of uv equal to 0 involves both u and v, dou f by dou u is not identically 0. So, if this relation is satisfied, it would mean that the expression in this bracket, that is dou uv by dou xy, is equal to 0. This must be the only possibility. Now we can show that this condition is sufficient as well. We are given that u and v are functions of x and y. So u is equal to u of xy, v is in fact v of xy. We can eliminate y from these two equations to obtain a new relation connecting u, v and x. Let it be capital F of u, v and x equal to 0. We need to show that there exists a relation connecting u and v which does not involve x or y explicitly. So if we differentiate this relation with respect to x, since this function contains x, we will get a term dou f by dou x plus, now we consider the effect of x in u, so that we get dou f by dou u into dou u by dou x plus, now that this function contains v which is a function of x and y, we will get dou f by dou v into dou v by dou x equal to the derivative of the right hand side, which is 0. Similarly, differentiating with respect to y, this relation gives dou f by dou u into dou u by dou y plus dou f by dou v into dou v by dou y equal to 0. Eliminating dou f by dou v from these two equations, we will get dou f by dou x into dou v by dou y plus dou uv by dou xy, that is the Jacobian of u and v, into dou f by dou u equal to 0. Since the Jacobian is equal to 0, we must have dou f by dou x into dou v by dou y. This first term must be equal to 0. Since the function v is a function of both x and y, dou v by dou y is not identically 0. Hence, we must have dou f by dou x equal to 0, which shows that the function f does not contain the variable x explicitly. Similarly, interchanging the role of x and y, we can show that capital F does not contain the variable y as well. Thus, we have shown that the condition is sufficient. That is, there does exist a relation connecting u and v which does not involve x or y explicitly. Next theorem states that if x bar is a vector such that x bar dot curl of x bar equal to 0 and mu is an arbitrary function of x, y and z, then mu x bar dot curl of mu x bar is equal to 0. Proof: we have assumed that x bar is equal to the triple PQR. So mu into x bar will be equal to mu p, mu q, mu r. By the definition of curl of a function, we can write curl of mu x bar is equal to the determinant whose first row is I, j, k. Second row will contain the entries dou by dou x, dou by dou y, dou by dou z, and the third row will contain the components of mu x bar, that is mu p, mu q and mu r. Expanding this determinant, we get this expression, and we can see that in the first term, if we replace I by j, r by p, q by r, similarly if we replace y by z, z by x, we will get the second term. And in the second term, if we replace these variables cyclically, that is if we replace j by k, p by q, r by p, similarly the variables z by x, x by y, then we will get the third term. So here we are changing p by q, we are replacing q by r, and then r is replaced with p. Similarly, for the variables x, y and z, the change is done cyclically, that is x is replaced with y is replaced with z, and z is replaced with x. So we can express the sum in this compact form: sigma I into dou mu r by dou y minus dou mu q by dou z. Now we know that curl of mu x bar is equal to sigma I into dou mu r by dou y minus dou mu q by dou z, as we have seen earlier, and this can be expanded using product rule. Then we get sigma I into derivative of mu r with respect to I is mu into dou r by dou y plus r into dou mu by dou y. Similarly, derivative of mu q can be expanded as mu into dou q by dou z plus q into dou mu by dou z. So, mu x bar dot curl of mu x bar, the dot product of these two vectors, will be equal to sigma, the first component of the first vector mu x bar is mu p into the first component of curl of mu x bar, that is the quantity inside this curly bracket, mu p into this function. Now we can take the first terms of these two expressions and group them together by taking mu square as a common term. Then mu square into sigma p into dou r by dou y minus dou q by dou z, minus, from the remaining terms we can take mu common, mu into sigma. Since minus mu is taken here, we can write p into this q into dou mu by dou z minus t into this r into dou mu by dou y. If we expand the sum in the second term on the right hand side, we get tq into dou mu by dou z minus pr into dou mu by dou y. The next term is obtained by replacing p by q, q by r, and r by p. And similarly, z is replaced with x, y is replaced with z. Thus we get the second term like this. And for the third expression, we replace q by r, r by p, and p by q. Similarly, x is changed to y, z becomes x. Then we get the third expression. We can say that pq into dou mu by dou z gets cancelled with minus qp into dou mu by dou z. Similarly, minus pr into dou mu by dou y plus pr into dou mu by dou y is 0, and qr into dou mu by dou x minus rq into dou mu by dou x is also equal to 0. So, this sum reduces to 0. Hence, in this previous expression, the second term on the RHS will be equal to 0. So, mu x bar into curl of mu x bar will be equal to the first term, mu square into sigma p into dou r by dou y minus dou q by dou z. And then we can expand this sum as mu square into p into dou r by dou y minus dou q by dou z plus q into dou p by dou z minus dou r by dou x by replacing r with p, q with r, y with z, z with x. Similarly, the third term is r into dou q by dou x minus dou p by dou y. And this expression can also be expressed as the dot product triple PQR dot this triple using the definition of dot product. And we can see that this second vector is in fact curl of x bar. So we have mu x bar dot curl of mu x bar is equal to mu square into x bar dot curl of x bar. So if x bar dot curl of x bar is equal to 0, then mu x bar dot curl of mu x bar is also equal to 0 if mu is an arbitrary function. And thus the theorem follows at once. The Pfaffian differential equation in 3 variables is said to be integrable if there exists a function mu of xyz with the property that mu into p dx plus q dy plus r dz is the exact differential d phi. And this function mu is called the integrating factor. And the function phi is called the primitive of the differential equation. Next theorem states that a necessary and sufficient condition that the Pfaffian differential equation x bar dot dr bar equal to 0 should be integrable is that x bar dot curl of x bar is equal to 0. So this theorem gives us a condition to test whether a given Pfaffian differential equation is integrable. For this, we need to convert the given Pfaffian differential equation into this form, x bar dot dr bar equal to 0, and then check whether x bar dot curl x bar is equal to 0. If this condition is satisfied, then the given Pfaffian differential equation will be integrable. The proof of this theorem is excluded in our syllabus. Next theorem states that given an integrating factor of the Pfaffian differential equation in n variables of the form x1 dx1 plus x2 dx2 plus etc. plus xn dxn equal to 0, then we can find an infinity of them. If there exists one integrating factor, then there will exist infinitely many such integrating factors. For the proof, let us assume that mu of x1, x2, etc. xn is an integrating factor of the given Pfaffian differential equation. Then by the definition of integrating factor, there will exist a function phi of x1, x2, etc. xn with the property that mu xi is equal to dou phi by dou xi, where I varies from 1 to n. Now, if capital phi is an arbitrary function of phi, we find that the given Pfaffian differential equation may be written in the form mu into d phi, d capital phi by d phi into the RHS of our Pfaffian differential equation will be equal to 0. Since small phi is a function such that mu xi is equal to dou phi by dou xi, we can replace mu x1 with dou phi by dou x1. Similarly, mu into x2 can be substituted with dou phi by dou x2 and so on. Mu into capital Xn will be equal to dou phi by dou xn. So that we get the new relation d capital phi by d phi into dou phi by dou x1 into dx1 plus dou phi by dou x2 into dx2 plus etc. plus dou phi by dou xn into dxn equal to 0. That is d capital phi by d phi into, this is the total differential of small phi into d small phi is equal to d capital phi, and that is equal to 0. So, this differential equation will have the obvious solution capital phi equal to c, which means that capital phi is also a primitive of the given differential equation. So, if mu is an integrating factor giving the solution small phi equal to c, and if capital phi is an arbitrary function of small phi, then mu into d capital phi by d small phi is also an integrating factor of the given differential equation. Since capital phi is arbitrary, capital phi may be any function. So, there are infinitely many integrating factors of this type. Thus, we have showed that there are infinitely many integrating factors of the given differential equation.